Hi, welcome to part 2 of my Kalman filter implementation for 6DOF IMUs. I mentioned last time that I'm using MATLAB. I often use Python as well, but this time I'm using MATLAB as a rapid prototype tool for showing the concept. In part 1, we developed a simple 1D, really an IMU model, gyro and accelerometer model, very simple. Part 2 here, I'm going to explain the complementary filter, how you use the complementary filter to estimate angles using gyro and accelerometer measurements. And then when we get to part 3, I'm going to extend it to the Kalman filter. So let's look at the MATLAB code. Last time I covered briefly how we set up the gyro. We're going to have to do the same, and accelerometer. We're going to have to do the same thing for the complementary filter, set up a couple of parameters, but it's very trivial here. We're going to set up a roll estimate at time k+1, so that's the current estimate, and then we're going to need a variable for the roll from the previous iteration, and I'll call that angle roll at time k. We also need two gains. The complementary filter is in a way it's kind of like an alpha beta or alpha beta gamma filter, which is a fixed gain filter, which is what this is. And we're going to mix together two different parameters. One that takes into account the sort of where the gyro thinks you are in angle, and we're going to let that be 99% of the solution. And then we're going to use a second gain that says, we know the gyro drifts, so we have to, let's use the accelerometer to correct for the drift. And so we're going to insert this little bitty piece of accelerometer measurement in here to help solve for that gyro drift and correct for it. An interesting thing to think about is while the gyros drift and accelerometers don't, the problem with accelerometers is that they tend to be very noisy. So if you've got a drone that's vibrating, and if you have too much of this gain here and take into account the accelerometer too much, that vibration will creep into the estimate of the angle. So it's one tricky thing about a complementary filter is you've got to play around with these gains and the hardware that you have to make sure that you get the angle and the stability that you want. So that's the parameters that we need. We go down to the actual loop now, the simulation, and it turns out it's only one line of code here. This is the code for doing the complementary filter. We're going to, all the complementary filter is the previous, we've got this first term I mentioned, which is the gyro part of it, and that part consists of the gain, the gyro gain, K1 here, which is, remember, 99%, times the previous, our previous estimate of roll, plus the gyro measurement. Remember, the gyro measurement is in degrees per second, so we've got to multiply that times delta t to find out the angle that we've traversed. And those together give us the total angle. Now we include the second term. Remember, I had it up there as only 1% of the solution, and that's the accelerometer measurement in degrees. So that's the entire required equation there for complementary filter. So let's see what happens when we run this. Let's go up and select Run. And here we get we get the complementary filter solution as compared to the true solution that we created in part 1 of the video of the series. So the blue line is the complementary filter, the red is original, and here this points out almost immediately one of the challenges with the complementary filter. And if I zoom in on this part up here, we can see that there's a slight lag of the complementary filter. And I mentioned that I could increase the gain in the accelerometer and try to remove some of that lag part. Also, it could be part of the bias, but that I would, if I do that, I might expect to see a noise in here on the accelerometer. So let's see if that happens. Let's go back and let's close this out. Let's go back to the gains, and let's make it 90-10, 90% and 10%. And let's run it again, and let's see what happens. And oh, it looks like sure enough we brought it together tighter. So let's see what happens with the noise, and see if we were right on the noise part here. Let's zoom in, same area, and sure enough, it's moved it up much closer to the 30 degrees. But there we're seeing that accelerometer noise creep in, and as long as you can keep that noise below some threshold, then you're happy with it. So that's the trade-off with the complementary filter. Thanks for watching part 2. I know I'm covering it fast, but feel free to take the code here and type it in and try it in MATLAB yourself and get a feel for how it works and play around with it, and you'll understand a little better. And hopefully by prototyping it in these 3 video series, we'll gain a better understanding of it, where we can then take it, port it over to our Arduino and an actual IMU and get it running in real time, and we'll understand it that way. Thanks again for watching.